Quantum mechanics has a problem physicists can't solve, and that's why it's so different. That's why even physicists don't know what it actually means. A 2025 Nature survey shows physicists disagree widely on what quantum mechanics says about reality. But why? What's the actual problem here? Why is it so hard to make sense of quantum mechanics? Hi, I'm a physicist, and this is the underlying problem of quantum physics. 100 years after the birth of quantum mechanics, the journal Nature asked over 1,000 quantum researchers a few questions, like, which of the following provides the best interpretation of quantum phenomena and interactions? And how confident are you in your answer? How would you answer? Please let me know. But if you're thinking, I have no idea what these interpretations are supposed to mean, let alone which one I prefer, you're not alone. I mean, the results are mixed. This theoretical physicist summarized the findings pretty well. She said, I find it remarkable that people who are very knowledgeable about quantum theory can be convinced of completely opposite views. I'd agree. But of course you could say, at least Copenhagen seems to be somewhat of a winner. But first, this is not really true, as we'll see in the end of this video. And second, among those who chose the Copenhagen interpretation, only about 50 people were confident in their choice. That's less than the people that were confidently choosing interpretations that aren't even on the list. And Copenhagen is the interpretation we usually start learning quantum mechanics with. It gets worse. Apparently, no interpretation seems to be really convincing. Only 24% of respondents thought their favorite interpretation was correct. Furthermore, people that chose the same interpretation disagreed on follow-up questions. So I'd say the results are we agree to disagree, or well, we have no clue. But how is this possible? Quantum mechanics is a well-established theory that's been around for a while. So you'd think physicists should have figured it out by now. To understand why that's not the case, to understand why it's so hard to make sense of quantum mechanics, we first need to get to the core of the problem. And therefore we'll compare it to classical physics. And then we'll understand why this debate is not settled. I bet you never heard someone discuss about the interpretations of classical physics. That's because most of the times there is just one. We're spoiled from classical physics. We're spoiled with obvious interpretations. We don't even have to think about how we interpret the math. Why is that the case? Let's say we describe some particles using classical physics. Then you can identify each particle through its position and momentum. If you know position and momentum, you have everything you need to know to make any kinds of predictions and to calculate other properties like kinetic energy. Mathematically, those properties are represented by functions. And the values of those functions are possible values of the properties. Possible values we could measure if we measure this property. And we might have some equations that relate different functions. Of course, we can stumble into some philosophical problems, but it's always obvious what the mathematical symbols are supposed to mean. Like we have a function for kinetic energy, so we can calculate the exact value of the kinetic energy the particle has right now. And if we measure it, we get this result. So there's a clear relation between math and reality. Each mathematical thing corresponds to a real thing. Like the function describing kinetic energy corresponds to the kinetic energy of a particle. Interpreting the math is straightforward. That's not the case in quantum mechanics. The math of quantum mechanics has no obvious interpretation. Why? Well, let's try to translate the classical interpretation to quantum mechanics. Then we'd say, instead of position or momentum, we maybe have a state vector that defines whatever we are looking at. So a state vector is the thing that describes the current situation. And instead of functions describing properties, we now have operators describing properties. If you don't know what an operator is, just think of a function. It's like a special kind of function. That's what we wish were the case, but unfortunately, it's not at all that simple. Why? Let's take a look at this vector. This is a state vector, so again, a vector that tells us something about the current situation. And this vector is spin up in x direction. And side note, yes, you can have spin up or down in x direction as well as in y direction or z direction. There's a spin in every spatial direction. So, this is spin up in x direction. Now, one could assume that this represents a particle with spin up in x direction. That's not wrong. But quantum mechanics has this thing. this thing that any vector can be expressed as a linear combination of other vectors. For example, this vector can be expressed as a linear combination of spin up and down in y direction. This is what physicists call a superposition. So you could also say this represents a particle that's in a superposition of spin up and down in y direction. I explained this in more detail in this video. Importantly, if you have a definite spin in one direction, this always means you have a superposition in the other directions. That's something that's not happening in classical physics. In classical physics, you can have definite angular momenta in different spatial directions. But what's even more important for us now is that in classical physics you can't just go ahead and rewrite an angular momentum in one direction in terms of a linear combination of angular momenta in other directions. But this must always be possible in quantum mechanics. So mathematically, spin up in x direction and superposition of spin up and down in y direction are the same thing. But clearly, to us, they're not. I mean, we can measure a spin up in x direction, but we can never directly measure a superposition. This feels like it could describe an actual particle. But this here, I mean, what's superposition even supposed to mean? And also, if we now use this instead of this, we do lose some information here. The information about spin up in x direction. So this kind of makes you doubt that this here describes something physically real. The bottom line of all this is, in classical physics we deal with vectors like position and momentum that are obviously related to something real. We directly know what they mean. In quantum physics we deal with things whose meanings we don't know. At first, superposition is nothing more but a description of something we don't know. That's what I explained in this video. So, we see that in quantum physics, not every mathematical operation automatically represents something real. And as if this wasn't already confusing enough, this also goes the other way. So we have a particle that's in a superposition of spin up and down in y direction. But you know that if we measure this, we won't see a superposition anymore. We will get a definite outcome. The thing is, and I feel like this is not talked about enough, this is not represented mathematically. There's no equation that tells us how this happens. There's no measurement operator. Measurement is not mathematically represented. So there are physically real processes that are not part of the basic mathematical formalism. And that's why quantum mechanics has an interpretation problem. Not every mathematical thing describes something real, and not every real thing is represented by some mathematical operation. Quantum mechanics has an interpretation problem. I mean, the math as a tool works well. It brought us things like quantum computers. But what the math is actually supposed to mean is far from obvious, as we've seen. So it's no wonder that physicists don't agree on what it's telling us. But shouldn't physicists be able to figure this out? I mean, it's been just over 100 years since the birth of quantum mechanics. Why is this debate not settled? What do you think? Before we go into this, it would be wonderful if you could leave me a simple like. It already helps a lot. And you can now hype my videos. This really supports a small channel like mine, so thanks for your hype points and your like. How do scientists usually figure out who's right? They come up with tests, experiments that verify or falsify their ideas. That's why it's super important that ideas must be testable or falsifiable in the first place. So there must be the possibility to prove them wrong, at least hypothetically. For example, the idea that quantum particles behave like classical particles is falsifiable. You can set up a double-slit experiment, and the resulting interference pattern kills the classical particle theory. Science moves forward. In quantum foundations, however, the theories, or actually the interpretations, are wrapped around this same mathematical core. They aren't predicting different results that could be tested. They are providing different narratives for why these results happen. Let's say we have a quantum coin that is either heads or tails when we look at it. Now, you know that the different interpretations of quantum mechanics don't just say it's gonna be heads or it's gonna be tails. Copenhagen says something like, the act of you looking at the coin forces it to be heads up. Many worlds say something like, there's a branch of the wave function where it's heads up and you see it being heads up, and there's a branch of the wave function where it's tails up and you see it being tails up. And Pilot Wave says something like, the coin was heads up the entire time, but it was hidden. How could you design an experiment to prove one of them wrong? Most interpretations of quantum mechanics are not testable, so our usual scientific toolbox doesn't work here. But then, how do physicists decide which interpretation to believe? Apparently, some just don't. The results of the Nature survey imply that many quantum researchers simply use quantum theory without engaging deeply with what it means. This isn't necessarily a bad thing. It just depends on your goals. I mean, just calculating still brought us quantum computers. So if you only need to use quantum mechanics as a tool, I can kinda understand why you don't care about the right interpretation. But of course, if you're into the philosophy or into quantum foundations, this is an important question. And interestingly, the researchers of these areas did not favor Copenhagen, not at all. They were the least likely to favor the Copenhagen interpretation, with just 20% selecting it. As soon as researchers apply thought experiments that probe more deeply, Copenhagen is not enough. This is something I'll talk about next week. But importantly, it shows that Copenhagen is really not a clear winner. There is no winner, because, as opposed to classical physics, quantum mechanics cannot be interpreted straightforward. That's because there are mathematical things that don't describe something real, and there are real processes like the measurement that is not described mathematically. This is the underlying problem of quantum mechanics, that it can't be interpreted easily. And that resulted into a huge number of different interpretations. Something I didn't mention yet is that choosing some interpretation always means that you have to sacrifice something from quantum mechanics. I don't have enough time to talk about this here, but if you want to learn more about this, please let me know. Importantly, it seems like we have no perfect interpretation yet. We agree to disagree. But we don't disagree on the fact that we need superposition. If you want to know why, check out this video. Thanks for watching. Have a wonderful day.